eigenvalues and eigenvectors, we have prescribed to 3 topics. One is diagonalization and the solving system of differential equations using the eigenvalues and eigenvectors, and then quadratic forms. Okay, reducing the given expression into the quadratic form, like that. These 3 aspects we will see in these coming classes. But particularly today we will plan the diagonalization and solving the system of equations, differential equations. Okay. So before going to that,
okay, sir.
I will give you some definitions, useful definitions. Is similar matrix. Similar matrix. Definition is matrix A is said to be similar. A is said to be similar to another matrix, say B, if there exists a non-singular matrix, say P, such that P is equal to P inverse A into P. Right? This is the definition. That A is said to be similar to B if there is a non-singular matrix P such that if that P giving you P inverse AP is equal to B or B is equal to P inverse AP, then A is said to be similar to B or vice versa. Okay? This transformation of A to B of A to B is called similarity transformation. Similarity transformation. Okay. Suppose if A is a square matrix of order n, has n linearly independent eigenvectors. N linearly independent eigenvectors. Then there exists a non-singular matrix P such that P inverse AP is a diagonal matrix. Okay, that is P inverse AP is equal to D. That means A and D are similar matrix. A is similar to D. Okay, understand? This matrix P is the transformation of the matrix, right? This P inverse AP giving you a diagonal matrix. If A is a square matrix of order n and it has n linearly independent eigenvectors, then there is a non-singular matrix P. So that constitute eigenvectors constitute P. Understand? Eigenvectors constitute P. Such P matrix will diagonalize the matrix A. That means here the matrix A is diagonalized. That resulting you a diagonal matrix. So this property or this statement will give a wide applications in the matrices in finding the power of the matrix, high powers of the matrix. Why? Because finding power of A is very difficult than finding the power of D, right? So using this expression or this statement, this result, so we can easily to find out the any power of A. Why? Because P inverse AP is equal to D. So from this I will give you the proof of that also, how we can find out the power of the matrix. So here we have to understood that the P matrix is diagonalizing the matrix A. This transforms the matrix P transforms the matrix A into diagonal matrix. The process of the transformation into diagonalized matrix is called the diagonalization. Okay, understand? So therefore the matrix which diagonalizes A is called, therefore here the matrix P which diagonalizes A is called model matrix. This P matrix is called model matrix, and the resulting matrix what is the resulting matrix here? T is called
diagonal matrix.
The spectral matrix. Okay, they are all the diagonal matrix. So therefore what are the diagonal matrix? Where the element or entries in the diagonal matrix are the eigenvalues. The set of all eigenvalues are called spectrum, right? So that's why it is called a spectral matrix, right? So whatever the triangular matrix, upper triangular matrix or lower triangular matrix or the diagonal matrix are having the eigenvalues or its principal diagonal elements. So therefore the diagonal matrix means it's having only diagonal elements. The diagonal elements are itself the eigenvalues. So therefore this D is called the spectral matrix, and the matrix which diagonalizes A, that means P, it is called the model matrix. P is called the model matrix. So now let's see how it helps the diagonalization, how we do the diagonalization. That means how this A is turning into the diagonal matrix. Let us see here. Let A be a square matrix. A be a square matrix of order n. Also, let lambda 1, comma lambda 2, comma so on. How many eigenvalues are there?
N.
Yeah, be the eigenvalues. And the corresponding eigenvectors, say x1 is equal to, I'm just writing u here, they are x11, x12, okay, so on x1n, comma, x2 is equal to x21, x22, so on x2n, so on xn is equal to xn1, so on xnn, right? Be the corresponding eigenvectors. Okay, they are linearly independent, corresponding. This is important. Linearly independent. This is, I think, linearly independent eigenvectors, right? So we assume A is the square matrix of order n and it has n eigenvalues. Eigenvalues are the scalars and the corresponding eigenvectors are assumed x1, x2, x3, so on xn. That elements will be, they are the vectors with n elements. X11 I just taken, x12 like this. Okay, now we show how this matrix A is diagonalized. So that implies when x1, x2, x3, so on are the eigenvectors corresponding to the eigenvalues lambda 1, lambda 2, so on lambda n of matrix A, means they will satisfy the equations, the definition of the eigenvalue and eigenvector. That is a1 x1 is equal to lambda 1 x1, right? Ax2 is equal to lambda 2 x2, right? So on Axn is equal to lambda xn, right? By definition of eigenvalues and eigenvectors. Now construct matrix P from the linearly independent eigenvectors. Construct P having the n vector, that x1, x2, so on xn, as the n column vectors. N column vectors. That is, P will be x1, x2, so on xn. Each vector, it acts as a column, one column. In each column, how many number of elements are there?
N.
N elements. And each row, how many vectors are there?
N vectors.
Yeah. So therefore, what will be its order? Right? P will be of order n by n. This is by, not x. Don't confuse. That is equal to, I am just writing here. That's why I am taken this x11 like. What is x1? x11, x12, so on x1n. This is x1. Now x2, x21, x22, so on x2n, so on xn1, xn2, so on xnn. Therefore, the matrix P is of order n by n, right? This is it. Now, P is equal to diagonal of, what are that values? Lambda 1, lambda 2, so on lambda n, right? See, now consider AP is equal to A into, what is P matrix? x1, x2, so on xn, right? That is equal to multiply with ax1, ax2, so on axn. Since by the definition of eigenvalue and eigenvector, ax1 is equal to lambda 1 x1, lambda 2 x2, so on, lambda n xn, right? So this you just construct, or you may be writing this also into the way that x1 lambda 1, x2 lambda 2, so on, xn lambda n, right? Because lambda is a scalar, you can write it whatever it is. So hence this can be written into the matrix form that as x11, means I'm just writing this product. These are the elements are there that will give you in the way that x11, x12, so on, x1n, x21, x22, so on, x2n, so on, xn1, xn2, so on, xnn, into the diagonal matrix which have lambda 1, 0, 0, so on, 0, 0, lambda 2, so on, 0, so on, 0, 0, so on, lambda n, right? Is it okay? The same which you are getting, the above step? Yes? Huh? This is P and this is D. So hence AP is equal to PD. Are you drawn this step? Clear? Understood?
Yes, sir.
Good. So now see this one. Now I just pre-multiply with P inverse and post-multiply with P. Pre-multiply with only pre-multiplication. Pre-multiplying. Pre-multiplying by P on both sides. Sorry, P inverse on both sides. Here, P inverse AP is equal to P inverse P into D, right? That is equal to that is equal to D. Hence, P inverse is equal to D, right? Therefore, the eigenvectors is not hello. Right. So therefore, what we understood here that A is diagonalized to D by the matrix P, where P is considered and constituted by the eigenvectors x1, x2, x3, linearly independent eigenvectors x1, x2, x3, so on, xn, right? And the eigenvalues constitute the diagonal matrix or the spectral matrix. So that is what we have written already, I think so. No, not written. We will write it here. The eigenvectors constitute the model matrix. P, and the eigenvalues constitute what matrix?
Spectral.
Spectral matrix. Spectral matrix D. Right? So in this way we can diagonalize the matrices. whatever that. So now how this diagonalization helps to find out the power of the matrix. So here calculation of power of the matrix. Powers of the matrix. Powers of a matrix. Okay. You see, we can calculate the power of the matrix. So we know that the matrix P diagonalizes the matrix A, right? So we have P inverse AP is equal to D, where A and D are similar, right? So from this we can write it that D or D square is equal to D into D, that is equal to P inverse AP into P inverse AP, that is equal to P inverse A into P inverse AP, right? That is equal to P inverse A into this A. What is A into A? This will be I. A into A is A square into P. That means what we have drawn is D square is equal to P inverse A square P. Similarly, in the same way, D cube is equal to P inverse A cube P. In general, we can write T power n is equal to P inverse A power n into P, right? Right, students?
Yes, sir.
Yes, sir.
P power n is equal to P inverse A power n into P. Now our aim is to find out the power of n, the power of A. So therefore, to obtain A power n, what we have to do? What we have to do to obtain A power n?
So pre-multiply P and post-multiply
Very good. Pre-multiply
P inverse.
P and post-multiply
P inverse.
Very good. So we get P into D power n into P inverse is equal to P into P inverse A power n into P inverse, right? Post multiply P and pre multiply P inverse. Sorry, pre multiply P, post multiply P inverse. So therefore, P into D power n into P inverse is equal to, what happened? This is equal to P into P inverse A power n into P inverse. P into P inverse is I everywhere in this and this. Therefore, it will be A power n, right? So therefore, hence A power n is equal to P into D power n into P inverse. Wherever you need to find out A power n, any power of the matrix A, it is sufficient to find out the P into D power n into P inverse. It is not needed to multiply all, because you know P, the model matrix, and D is the diagonal matrix, and P inverse is the inverse of matrix P. So what is the difficulty here? You see, here P matrix is there, P inverse is there, that is okay. Where D power n, it is very easy to find out power of the diagonal matrix, right? power of the diagonal matrix. Because suppose D is equal to say lambda 1 0 0 lambda 2. So what is D square?
Lambda 1
Lambda
square
1 square 0
0
0
0 lambda 2
lambda
lambda
square.
2.
So whatever the power of D power n is equal to lambda 1 power n 0 0 lambda n power lambda 2 power n, right? It is very easy to find out just the powering of the diagonal elements, which resulting you D power n. So therefore, that D power n can be pre multiply with P and post multiply with P inverse. It resulting you the required any power of n power, right? This is the main application for finding the power of the matrix. Suppose if there is needed to find out a power 5 or a power 6, a power 7, you needed to find out every time that multiplication, right? But where the higher powers of a can be determined using this diagonalization concept. Okay, right?
Right, sir.
Yeah. Here one more main thing is here. First, to find out the linearly independent eigenvectors for the corresponding eigenvalues. For the corresponding eigenvalues. That is very important. You have to properly find out the linearly independent eigenvectors. If they are not independent, you have to make them, you have to find them the n linearly independent eigenvectors only. Then only you can possible to construct the model matrix P. If they are not linearly independent, the P matrix cannot diagonalize A. Understand? Right? This is very important point. So in such case, I would like to give you one more point here. Suppose A is a real matrix, a real symmetric matrix. A is a real symmetric matrix with n pairwise distinct eigenvectors. N pairwise distinct eigenvalues. Eigenvalues. Say lambda 1, lambda 2, so on, lambda n. Pairwise distinct means distinct. If you take any two, they are not equal. Right? That generally we maybe use n pairwise distinct eigenvalues. That's all. That means distinct eigenvalues. Nothing is there. Then the corresponding eigenvectors x1 comma x2 comma so on xn are pairwise orthogonal. Pairwise orthogonal. You know what is meant by pairwise orthogonal? Because x1, x2, x3, so on, xn. If you take any two, that means xi transpose into xj. Is not equal to, is equal to 0. Is equal to 0. Where I comma j not equal to, I is not equal to j. Okay, then only we can compare with the both. The x1 is compared to x2, x2 is either the orthogonal or not. X1 is orthogonal to x2 or x1 is orthogonal to x3, whatever it is. So you can check it whether these two are orthogonal or not through this statement. That means x1 transpose into x2. If it is equal to 0, then we say that x1, x2 are pairwise orthogonal. Are orthogonal. Okay, this is orthogonal means, right? In such case, when these orthogonal matrices, orthogonal vectors also constitute the model matrix P, but that P matrix cannot diagonalize. So in such case, you consider P is equal to in this case only P is equal to matrix with the elements E1, E2, so on, En, where E1 is equal to x1 by norm x1. Understand? E2 is equal to x2 by norm x2. Okay? Yes. For the real symmetric matrix, the distinct eigenvalues resulting you the orthogonal eigenvectors, pairwise orthogonal eigenvectors. So in such case, the P model matrix to be considered as describing with their norms. You know, norm vector, how we can define the norm vector? En is equal to xn by norm xn. Norm xn, where norm x, okay, is defined as square root of x transpose into x. Norm x is defined as square root of x transpose into x. Okay, x1, suppose norm x1 you need to calculate. X1 is a vector, it has n elements, column elements, right? Where the norm x to be determined as square root of x transpose into x. The multiplication, the matrix multiplication is compatible in such case, right? 1 by n, one matrix and another matrix n by 1. So that matrix compatibility will be satisfied, right? Suppose I just started taking U here, A, B, C. Then norm x is equal to square root of x transpose into x, that is equal to root of x transpose is A, B, C into x is A, B, C. That is equal to root of a square plus b square plus c square, right? That resulting is the distance from origin to the point. Okay, understand? These students?
Yes, sir.
Yes, sir.
Clear. So in such case, we have to find out we have to constitute that P as with the norms. Okay, good. So in such case, we are using these all the pairwise orthogonal eigenvectors for constituting the model matrix P. Then that P will be orthogonal matrix. P will be orthogonal matrix. So in such case, this case, P will be orthogonal matrix. So how we can say P will be orthogonal matrix means that is P transpose into P is equal to I. That is equal to P into P transpose also, right? P into P transpose or is equal to P transpose into P is equal to I. Then we say that P is an orthogonal, no? Any matrix. Or
Yes, sir.
P transpose is equal to P inverse, right? Or P inverse is equal to P transpose. If any matrix is orthogonal, then its P inverse, its inverse is equal to its transpose, right? So therefore, the diagonalization property. What is the diagonalization property? P inverse AP is equal to D, right? This becomes for the orthogonal matrix P, but P inverse is P transpose A into P is equal to D. Right? If P is orthogonal, then P transpose AP is equal to D. Understand?
Yes, sir.
Yes, sir.
Yeah, in such case, we can find out the all diagonalization and the problems. So we will see it here, the problem, how we can diagonalize that. So there I would like to show you. Yes. Is my screen visible to you? This is what the diagonalization it has been written, everything. You go ahead on that way. Here everything it is. I just showing you the example. One example. Yeah. Show that the matrix, given matrix, 1, -1, 2, 0, 2, 3, 0, 0, 3 is diagonalizable. Hence find P such that P inverse AB is the diagonal matrix and find A for 5. You see it here. So first we find out the eigenvalues and eigenvectors for the given matrix. First check it whether it is a symmetric matrix or not. This is not a symmetric matrix. So therefore find out its eigenvalues and eigenvectors. So for finding eigenvalues, the characteristic equation is A minus lambda I is equal to 0. Finding there the eigenvalues which has been obtained for the given problem are 1, 2, 3. Since A has 3 distinct eigenvalues, okay. So and the corresponding eigenvectors to be determined. So for lambda is equal to 1, the eigenvectors are, see it here, yeah, this one is 0. This is 0, right? This is x1 is 1, 0, 0. So therefore this P is this one 0, 0. Okay. Please find the correction in your file also that we have uploaded, because when it result in you the equation, it has been to apply again one more one more operation in R2. This you make it 0, and in R3 finally you make it 0. So therefore it results in you here the rank of the matrix is 2. So therefore one arbitrary constant, one arbitrary solution will be there, that they have been considered x is equal to an arbitrary and yz is equal to 0 from that. So therefore the eigenvector is 1, 0, 0. Similarly, for lambda is equal to 2, eigenvector is 1, minus 1, 0. Lambda is equal to 3, the eigenvector is 1, minus 6, 2. This you know. So therefore then the model matrix P is equal to, what is P? x1, x2, x3, right? x1 is 1, 0, 0, x2 is 1, minus 1, 0, x3 is 1, minus 6, minus 2. So now find out its inverse, P inverse. For that, determinant of P calculated. Now P inverse A into P. Once you have P and P inverse, now find out P inverse AP. You have to multiply this one, all these three matrices. P inverse AP. That P inverse AP is equal to, it has been obtained 1 0 0 0 2 0 0 0 3. It's clearly diagonalized. Yes, it's clearly diagonalized. Now finding A power 5. So you know what is how we can find out the power of the matrix? We know A power n is equal to P into D power n into P inverse, right?
Yes, sir.
Apply that one. We need to find out A power 5, therefore putting n is equal to 5. A power 5 is equal to P. P matrix is there, here 0. Right? 1 0 0 1 minus 1 0 1 minus 6 minus 2 and D power 5. D is this one and D power 5 is only their principal diagonal elements power will be extended to 5. So therefore 1 0 0 0 2 power 5 0 0 0 3 power 5 1 by 2 P inverse is this much. If you multiply this one, this is the required A power 5. Okay. So this way you can do the power of the matrices and the diagonalization.
Yes, sir.
Any doubt in this? Any doubt in this diagonalization? So like that, the same problems are there, other problems. So you can easily to go in that diagonalization, all of them. Same, finding eigenvalues and their corresponding eigenvectors and construct the model matrix P with the eigenvectors, find out its inverse and P inverse AP to find and show that that is equal to D. Okay, that is equal to D. Already we have.
So can you please tell that here what is linear independent term means?
What is linear independent?
Yes,
How
sir.
we can say that
Here
all
the
the
condition
vectors
now.
is linearly independent. That determinant is not equal to 0, right? Determinant of all the elements not equal to 0. That is one thing. Or you maybe use the definition alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 is equal to 0. Huh? Is equal to 0 if all alpha
Yes,
is
sir.
equal to 0.
Yes,
All
sir.
alpha is equal to 0. That definition. Okay. This is
Okay,
diagonalization
sir.
and finding the eigenvectors. Finding the powers of the matrix. Now quadratic form, we will look this quadratic form in the next class. I will go for the solution of solution of first order equations, right? Differential equations. Solving system of ODEs. Okay?
Okay, sir.
See that one. Solve the system of ordinary differential equations. Let us consider a first order linearly homogeneous system with constant coefficients as such follows. x1 dash is equal to a11 x1 plus a12 x2 plus so on a1 and xn. x2 dash is equal to a21 x1 plus a22 x2 plus so on. So this system can write into the matrix form as x dash a into x, right? Where a is the coefficient matrix of order n by n and x is the column vector as n. Now, for solving of this system in the matrix form, x dash is equal to ax. So the solution will be x is equal to v bar into e power lambda t. Right? How the solution will be like this? You can understand. Where x is the vector and that is also a solution vector, right? We have to find out the solution of this system means we have to find out x, where x is the vector. and vector. That what is x there? Can anybody say here? I'm writing here. Sorry, x1, x2. X is equal to x1, x2, so on, xn, n column vectors, right? This is a vector. So now this our differential equation is of form like this: y dash is equal to ay. So this is the first order equation, first order differential equation. By separating the variables, we can solve very easily. So therefore, its solution will be y is equal to c into a power x, right? Where c is the constant of integration, a is any scalar, any constant, the given constant, y dash is equal to ay, right? The solution is y is equal to c into ax, where what is the c? What is c?
So constant.
Yeah. How we can obtain the constant?
So by t putting that e raised to power in that x0 in that equation.
Very good.
Y is equal to c e raised to
So
power
here
ax.
c is not the constant. Not only here, everywhere where the given differential equation of form y dash is equal to ay, then the solution is y is equal to c into e power ax, in which the c is the initial solution, we can say, right? That means when x is equal to 0, y is equal to c. So therefore, that c is the initial solution of the problem when x is equal to 0, right? Right? Where c is also the solution when x is equal to 0 for the given problem. So therefore, c is the solution at x is equal to 0. At x is equal to 0, y is equal to c is also the solution. But our solution is a vector x, right? So therefore, c must be a vector. In our case, for the solution of x dash is equal to ax, our solution will be of form x is equal to some c into e power some constant into t, right? So therefore, it will be a c will be a vector. So that's why I have taken here the solution will be v bar. This is the vector into e power lambda t, where lambda is the scalar. So our solution will be of form x is equal to v bar e power lambda t, right? This system x dash is equal to ax has a solution x is equal to v bar e power lambda t, right? This will be a scalar, this will be a vector. Is any doubt in this vector and scalar? That solution it's clearly of form x is equal to some constant into e power some constant x or t here, whatever it is, right? Are you understand, students?
Yes, sir.
So now check it. What is this vector and what is this lambda? Suppose if this is the solution, it must satisfy the differential equation. So now when x is to be a solution, then it must satisfy this equation. That means x dash is v bar and it is differentiating with respect to t, e power lambda t into lambda. So therefore, v vector lambda into e power lambda t, that is equal to a into x, v bar e power lambda t. So this we can simplify, that resulting u form a minus lambda I into v bar is equal to 0. Why? Because e power lambda t you take it common and this is not equal to 0, this is an exponential function, right? So what is this indicates? You just see what this indicates. A minus lambda I into v bar is equal to 0. Now we conclude here what is the representation of lambda and V bar. Here we seen that this system has the solution of form x is equal to V bar into e power lambda t. That is no doubt at all, it is very clear. But now we will signify what is V bar and what is lambda. So for that we have taken this as the solution of for that and drawn the statement that a minus lambda I into V bar is equal to 0. It's very understood. This statement describes a non-zero solution V bar is the eigenvector corresponding to the eigenvalue lambda, right? Right? This is the eigenvalue
Yes,
problem. This is exactly the problem of determining the eigenvalues lambda and corresponding eigenvectors V bar of the matrix A. So you have been very clearly understood that any system of ordinary differential, first order differential equation ODE of first order, which has the solution of form x is equal to V bar into e power lambda t, where V bar is the eigenvector corresponding to the eigenvalue lambda. This is only the understanding concept and very key point for solving the first order ODEs using eigenvalue method. Eigenvalue method means using eigenvalues and eigenvectors. Eigenvalue problem. Okay. Now see. So there are many eigenvalues and eigenvectors are there. So therefore, say x1, x2, x3, so on, xn are linearly independent solutions. Then what will be the most general solution? The most general solution will be x is equal to c1 x1 plus c2 x2 plus so on cn xn, right? Right? The most general solution will be x is equal to c1 x1 plus c2 x2 plus so on cn xn, right? If x1, x2, x3 so on
yes,
are
sir.
the independent solutions, then their linear combinations are the most general solution. So each x1 or the solution, that is each x1 is v1 bar into e power lambda 1t, and x2 is v2 bar into e power lambda 2t, so on plus vn bar into e power lambda nt. Like that, most general solution can be obtained. For showing that linearly independence or dependence, you can see determinant of x1, x2, x3, so on, xn is not equal to 0 because they are independent. If it is equal to 0, they are dependent. Okay, that is. Now see the problem. Solve this system of equations. X1 dash is equal to 3x1 minus 2x2 and x2 dash is equal to 2x1 minus 2x2. This is the given system. Now first write this one into the matrix equation. Consider x is equal to, let x is equal to, here what are the unknowns? x1, x2, that we put it in the vector. X is equal to x1, x2, right? So therefore, the given system can write into the matrix form x dash is equal to 3 minus 2, 2 minus 2 into x. X is again x1, x2. So where a is equal to 3 minus 2, 2 minus 2, right? This is the matrix A. Now find out its eigenvalues. Eigenvalues are 2 and minus 1. You know, determinant of a minus lambda is equal to 0. Find out its characteristic equation and their roots are the eigenvalues. Lambda is equal to 2 and minus 1. Now the corresponding eigenvectors for each eigenvalue. Lambda is equal to 2, eigenvector is 2, 1. Right? If eigenvector is 2, 1, then first eigenvector, next second eigenvector for lambda is equal to minus 1 is 1, 2. So hence the solution is x1 is equal to v1 into v1 bar, that is a vector. v1 bar into e power lambda 1 t. That is equal to v1 is the first x1. First v1 bar is equal to 1 into e power 2 into t, and x2 is equal to v2 into v2 bar into e power lambda 2t, where lambda 2 is minus 1. So v2 is 1 to e power minus 1t, right? I hope two solutions are there. Now let us check it whether they are independent or dependent. Find out their determinant. Determinant of x1, x2. x1 is 2 e power 2t, 1 into e power t. x2 is 1 into e power minus t and 2 into e power minus t. So determinant you find out, this is not equal to 0, right?
Yes,
So
sir.
hence they are linearly independent. Then what is its solution? Most general solution, C1 x1. Most general solution is
So C1
C1
x2 plus
x1
C2 x.
C2 x2. So C1 x1 is 2 1 e power 2t and C2 x2 is 1 2 e power minus t. So therefore this is x. So general solution x is equal to, x means what is x? What is x? Vector here, x1
Eigenvector.
x1 x2 right, vector is equal to this. You can write it c1 into 2 e power 2t, c1 into e power 2t plus this one you can write c2 into e power minus t, 2c2 into e power minus t, right? So then you can get it that solutions x1 is equal to 2c1 e power 2t plus c2 e power minus t. x2 is equal to c1 e power 2t plus 2c2 e power minus t. This is the required solution x1 x2, right? Any doubt in this? Finding the solution here, key points are only, first write down this given system into the matrix form, x dash is equal to ax, and its solution will be assumed x is equal to v bar into e power lambda t, and where v bar is the eigenvector corresponding to the eigenvalue, that the solution will be most general solution c1 x1 plus c2 x2 plus so on cn xn. That is, first write down its matrix form with the vector solution vector x is equal to x1 x2, assuming find out eigenvalues corresponding eigenvectors. That solution will be v bar is equal to v1 bar is equal to the eigenvector into e power lambda 1 t, x1 x2. Okay, any doubt in this? The same way you can do the problems. Here I have given, right?
Yes, sir.
Please go through after the class so you can understand very clear the solution of differential equations with eigenvalues and eigenvectors. Good. Okay. Thank you.
Yes, sir. Thank you, sir.
Thank
If you have any doubt, you can discuss.
Thank you, sir.
Good.
you.
Thank you, sir.
Thank you.